Viscosity. Fluid properties such as density or specific weight helps us get the idea of heaviness of the fluid. This proved to be not sufficient enough when we observe oil or water having closed densities but very different flow phenomenon. Thus an additional property is required to describe this fluidity of the fluid. Let us explain it with a hypothetical experiment. Consider two flat horizontal surfaces such a fixed plate and a free plate, connected with each other through a medium in between. The thickness of this medium is given by small b. Imagine a line AB across. When force F is applied, the free plate moves moving point B to a point B dash, thus traveling a distance of del A. When force is applied on free plate, it will tend to move. If material is solid, the deformation, angular, will occur as del beta here. A stress will originate due to force applied. For equilibrium, F is equal to shear stress times area, and shear strain is proportional to shear stress. But if the material is liquid or fluid, as per the definition of a fluid, the upper plate move continuously with velocity u. At the same time the lower fixed plate is at zero velocity. A gradient is formed from one plate to the other plate. This shows that velocity u is a function of y or lateral direction. This helps us quantify the velocity gradient as u equals u over by, which implied du over dy equals to u over b. Keep note that this is valid when assuming fluid sticks to plates, no slip condition. For small time interval, del t, the line AB rotates del beta to AB dash so that tangent del beta equal del A over b. We know for small angles tangent del beta become del beta. Thus we get del beta over del t equal to u over b. For solids, shear strain is proportional to shear stress. But here angular deformation depends on velocity caused by the force and depends on time. Further experimentation shows shear stress is directly proportional to rate of shear strain. This is valid for fluids only, where tau is proportional to del beta over del t. This rate of angular strain is equal to velocity gradient. Thus we get constant of proportionality defined as viscosity. Mu is absolute or dynamic viscosity, given by FL-2T or ML-1T-1. If we plot the relation of viscosity, the steeper shows more viscous fluid, which means large stresses will create little change in velocity across the fluid layers. Fluids that obey this relationship are called Newtonian fluids, where shear stress is linearly related to rate of shear strain. Non-linearly related are non-Newtonian fluids. Slope of shearing stress are donated via apparent viscosity. Mu AP is independent of shear rate. Shear thinning. Apparent viscosity decreases when shear rate increases. Colloidal suspensions, polymer solutions. Harder the fluid is sheared, less viscous it becomes. Paint on a brush does not drop but flows on wall. Shear thickening. Apparent viscosity increases, shear rate increase. Harder fluid is sheared, more viscous it become. Common examples include cornstarch mixture, quicksand. Then there exists a special kind of fluid called Bingham plastic. Bingham plastics act as solids, they have no flow until threshold, after which is flows like Newtonian fluids. You can see this in our daily life such as toothpaste, mayonnaise. For liquids, viscosity decrease with increase in temperature. If water temperature rises from 20 to 38 degrees Celsius, density drops only 1% but viscosity drops to 40%. For gases, it is vice versa. For gases, viscosity increases with increase in temperature. Exchange of moment between low bulk velocity and high bulk velocity of gas molecules. Resistance in relative motion between layers. For liquids, Andrade presented this equation where D and B are empirical constants. For gases, Sunderland equation has C and S as empirical constants. Last thing to note here is an expression called kinematic viscosity, which is absolute viscosity over density, represented with nu dimensionally L square T minus 1. Thanks for watching. For further lectures go to AACOE Online. And don't forget to subscribe.